In this video, we're going to talk about the speech signal and try to understand its structure. That structure is exploited in all kinds of systems, including modern telephone systems and cell phone communication systems. It's really important to understand the structure. It's one thing to have a general characterization like what bandwidth, what kind of frequencies does the speech signal occupy, but there's more structure beyond that that's going to be very important in designing efficient communication systems for speech. So all the aspects of the speech signal are determined by how it's generated, and we're going to develop a model for that that's based on linear signals and systems, things we already know. And this is going to lead us to look at the spectral structure of speech. Turns out in the time domain you can only gain so much information from examining a speech signal. But if you look at its spectrum, you look at its Fourier transform, then all of a sudden a lot of information pops out that's very, very useful in understanding what is going on and what is being said. So, how is speech generated? So here's my rather crude drawing of the speech production system. Everything begins with the lungs, and the lungs are providing a source of air pressure. And the important part for us in understanding speech are the vocal cords. Now, seen from the top, the vocal cords look like the structure looks something like this, where these are tendon-like things, and in between there's a slit that's open. And when you breathe, the vocal cords, this part, is not under any tension. They're loose. The slit opens up and you breathe normally. When you want to say something, what happens is that these come under tension. They're pulled. And that closes up this slit. All right? And in fact, they become completely closed. And it's not until the air pressure from the lungs builds up enough that forces this slit to open momentarily, releasing a puff of air, which goes into the vocal tract. The vocal cords close, air pressure builds up again, they release rather quickly, giving another puff of air, and that's what I've tried to indicate there. So if you were to plot, as a function of time, the air pressure just above the vocal cords, you would get nothing for a while because the pressure below is building up, and finally it releases, releasing that puff of air, and it comes back down. And then the pressure builds up from the lungs again, and it pops up again and releases. And roughly, it produces a periodic, pulse-like sequence from the vocal cords. And this period is known as the pitch period. And we're going to talk more about that in just a second. Well, now what happens is that these puffs of air go into what's called the vocal tract, which is formed by all of these structures: the tongue, the lips, the opening of your mouth, all kinds of things. And if I were to draw this again, so we might have something that looks like this, opens up, has some teeth here at the end. And what's happening, those puffs of air coming in there. Well, what acoustically, what your mouth looks like is a pipe. It looks like, if I was to straighten this out, it would look like a pipe who has a cross-sectional area that's varying. So this is the length of the pipe, and this is its cross-section. And acoustically, your mouth looks like a straight pipe which has a complicated structure. Well, what happens now is the air pressure signal comes in here, and the word is excites the air pressure inside the vocal tract. Well, that turns out we can describe this as a linear filter having peaks that are called resonances, and this functions in many ways like an organ pipe. Organ pipe is a straight tube, has a very simple resonant structure. The way a note sounds on an organ is you push the key, what happens, air is forced into one of those pipes, and it gives you this nice, not quite pure tone, but resonant structure having harmonics of some fundamental. Because of the variable cross-sectional area here, it turns out the resonant structure is a lot more complicated, and that's what we're going to see in the next slide. So let's summarize what the speech model is, at least in terms of a system theoretic model. So we have the lungs, and what they're producing is actually a pretty boring signal. It's basically a constant. The vocal cords will either be open while you're breathing, or they will be put under tension when you're trying to speak. And that means there's some neural control coming from the brain that's controlling that. Then that, for the point of view of speech, is the only thing we care about. That produces what we're going to describe as a periodic pulse train, a periodic pulse sequence, something we've already talked about. That serves as the input to the vocal tract, which, according to what you want to say, the position of the tongue, the lips, everything else is again under neural control, and that determines what is being said. And the result is the speech signal that you pick up with a microphone. Well, let's examine this in more detail to figure out important characteristics of these signals. So here's that model again. And I want to start with the input here, the periodic pitch signal, which is a periodic pulse train. We've already talked about this many times. So it consists of a set of pulses quite narrow, and T is what's known as the pitch period. But what people normally refer to as the pitch is the pitch frequency, which is 1 over T, and in the speech world that's called F0. And that's the pitch. So as you change the tension of your vocal cords, you can make your pitch go up or go down if you loosen it. And that's all, again, under neural control. Now, that signal serves as the input into what we're going to describe as a linear filter, which has a transfer function which will change according to the vowel or the speech sound you're trying to make. So I have here two vowel sounds that I chose, the O and the E, and this is what I'm plotting here is the transfer function of the vocal tract. So an O sound has a series of peaks. These are the resonances I was referring to before. And so does the E sound. It has a series of peaks, but you can see they have a very different structure. And let's look at that structure in more detail. In the speech world, each of these peaks is called a formant. And the formants are determined by their frequencies, which are just numbered sequentially. So the lowest, the frequency of the peak at the lowest frequency is called F1. The next higher up is called F2. The next one's F3 and F4. So they're all just numbered sequentially according to the order they appear from low to high in the speech spectrum. So the O has a moderately high F1, a very low F2, F3 is shifted up, making a nice valley, and then there's F4 and F5. For the E sound, F1 is lower than it is for the O. F2 is all the way up here. So that resonant structure has really changed a lot. F3 is a little higher than it was for the O, and then F4 and F5 are roughly at the same place. So you can actually look at these spectra and figure out what the vowel is that's being said. Now, if you look in the time domain, things are not quite so clear. Here is a segment of a speech corresponding to me saying O, and a segment of speech corresponding to me saying E. Now, what you should recall is back when we talked about sending this periodic pulse sequence through our RC low-pass filter, what we got out was, again, something that was periodic, kind of looked like this. And so we should expect something similar here. We have the same pulse sequence going into a linear filter. It's a bit more complicated than a simple RC low pass, but again we should see a periodic output. So I used this example at the beginning of the course when we talked about signals, and you should be the period should be readily evident. I'd like you to tell me what the period is for the vowel E in this case. Okay, I get a period of roughly 10 milliseconds. This scale is in seconds. The separation between these peaks is about 10 milliseconds, which makes the pitch 100 hertz. Now, another question for you. Let me clear the slide so we can see things. What is the pitch here? And in particular, is it higher or lower than it is for the E? And when I talk about pitch, we really usually worry about the frequency, not the interval, but the frequency. Is the pitch frequency lower or higher for the O? Okay, I think it's pretty evident that the pitch is frequency is lower because there are fewer, there's only one period there, and I see at least two there. So in a shorter period of time. So the pitch is lowered a little bit below 100 hertz. So what should we expect the spectrum of the speech to look like? Well, as we know, the spectrum is equal to the transfer function times the Fourier transform, in this case the Fourier series of the pitch signal. So you should expect the transfer function h of f, which is one of these, to be multiplied times the Fourier series for this, which consists of a set of harmonics. The harmonics are all harmonics of f0. So our model for speech is a little bit simpler than what I've shown. We just worry about what the pitch signal is, basically what its period is, what its pitch frequency is, and then we worry about what the transfer function is, and that is how we describe the speech signal. And let me show you what an actual speech spectrum looks like, and now it makes a little bit more sense what we're seeing. So you can see these peaks in the spectrum, and that corresponds to the pitch, right? Because it's going to have the spectrum of our periodic pulse train is going to be a set of lines decaying like a sinc function at the harmonics of f0. So that would be at f0, 2f0, 3f0, etc. And that corresponds to each of these peaks. And they will go out forever, but generally go down. In some places, it gets rather hard to see that peak structure, and that's because the energy is getting rather low. And furthermore, that departs from the shape of the transfer function a little bit, and that's because the sinc function character of the Fourier coefficients is reducing it. And so you can see that the amplitude of these pitch lines is multiplied by something that does look like the transfer function for the letter O. And so now we can see what's going on. We should be able to look at a spectrum and see what the pitch is and get a rough idea what the formant structure is, at least saying generally where's F1, is it high or low, is F2 really high or really low, and I think you can see that fairly easily from this plot. That's why in this frequency domain, speech, the structure of speech is much more apparent than it is in the time domain. All right, so here is what we call the speech spectrogram. And this is a special plot that plots frequency on the vertical axis, and what it's plotting at each moment in time is a spectrum as a heat map. So there's a spectrum corresponding to each column of the image here, and the amplitude of the spectrum is encoded as a color. So the very deep red corresponds to the highest amplitudes, the yellowish are smaller than that, the greens are even smaller than that, and the blues are the smallest areas. Essentially the temperature reflects amplitude, and that's why it's called a heat map, of course. All right, so what we see below is the time domain plot of the speech signal, and that's me saying Rice University. And there are some segments in which you can roughly make out the periodic nature of the speech signal. The scale here is highly compressed. We're going over 1.2 seconds, so it's very hard to see. What's much clearer is what's going on in the frequency domain. It makes everything much clearer to me. So the first thing I want to point out are these lines across here, and we now know those are the pitch lines. That corresponds to the pitch. They're harmonics of the pitch. Over here, it looks to me like the pitch is going up, right? Because the lines are moving up to higher frequencies. So that's me saying rise, rise. Here it looks like they're going down a little bit, and over here they're relatively constant. So you can get an idea of how the speaker is saying the words by looking at those pitch contours. Now, what's more important to understanding, at least in English, what is being said are the formants. So I see here that's probably F1, here's F2, so F1 is relatively constant, F2 is moving up, this could be F3, and then over here could be F4. Here you can see F2 really moving up, F1 maybe moving down a little bit, and here's F2 really moving up, and F1 moving down when I'm saying T. And so we can get a very detailed idea of what's going on in the speech signal. In fact, there are experts out there that if you give them a spectrogram and tell them what the language is being spoken, then they can tell you what's being said and whether it's a male or female that's saying it. Because I know it's me, I have some idea of scale, and I can tell you the pitch is much more indicative of a male than a female. Females have a higher range of pitch frequencies than males. This one is low, about 100 hertz. That probably is a male. If it goes much higher than about 120 hertz, then that's probably a female, and children are even higher. Now, I want to point out some things, and that is there are some aspects of this that don't fit the speech model and don't have pitch lines, and that's corresponding to these areas. And that's when you're saying s, si, and that corresponds to what we call fricatives. These are words in which the vocal cords open up, the lung air pressure from the lungs just hits the vocal tract, and then by closing the teeth or the lips, you create essentially a turbulent noise. It doesn't have much structure in the time domain, but in the frequency domain it occurs at high frequencies. In this plot it is occurring higher than any of the formants, and that is pretty typical. It's very interesting that in the old days, in the days of analog telephones, that they would filter speech signals at about 3,300 hertz. So they would low-pass filter the speech signal with a cutoff frequency of about 3,300 hertz, cutting out everything above that. Now it turns out that is high enough that it doesn't really affect the formant structure all that much, at least in terms of understanding what's being said, but for the fricative signals it definitely makes it very hard. I know in the old days it was very hard to tell words apart that differ only in their fricative. Fix and six were incredibly difficult to tell apart over old telephone systems, and in fact I suggest you try it with a friend. Call them up and say these words in isolation and see if your friend can understand what you're saying. Now of course if you put these in a sentence you can easily tell them apart. You can say, I fixed my car. You certainly would not say, I sixed my car. It doesn't make any sense. So if you say them out of context, in isolation, one word at a time, I think you're going to find, in some cases, you're going to have a hard time telling them apart. If your phone system has a much higher cutoff frequency, then those get through. So you can judge what's going on in the phone system by playing a little word recognition game. Now, there's something else I want to point out here, and that is the highest frequency in this plot is about 5,500 hertz. And we'll go into why that is when we talk about digital signal processing. It turns out there are some signals, speech signals, that even have higher frequency content, and we usually say the bandwidth is about 6 to 7 kilohertz. It's very approximate because, as you've seen, the transfer function for the vowels is going down as frequency goes up generally. Beyond about 4 or 5 kilohertz, it's definitely going down. So the bandwidth is only a rough measure of what's going on. So we now can see a lot of things about the structure of speech. Now I claim that if you look at the spectrogram, there's something not speech-like in the spectrogram. There's something here that isn't right. And in particular, I want to point out this line. It's going across here. What in the world does that correspond to? There are two answers. One is what kind of signal would produce that line, and what's physically producing that line. Okay, well, physically what that looks like in terms of signals, it turns out it looks like a sine wave of a frequency of about 1,800 hertz. Well, that's pretty high. It's certainly not power frequency, and it turns out that's fan noise from my computer. I couldn't get my computer to turn its fan off when I made this recording, and you're picking that up, and you can even see there's another piece of it up there at a higher frequency. Okay, so we now know what the structure of speech is. First of all, it has a bandwidth of about 6 or 7 kilohertz, and that's important in many applications. The structure of speech is best seen in the frequency domain. There are some time domain things you can pick out, like what the pitch period is. That could be pretty easy, but it's hard to see how pitch is changing very easily with time until you look at the spectrogram, look in the frequency domain. Now, I want to point out that many other signals share the same frequency range as speech. And signal processing systems they exploit in great detail the special structure of speech so that they can send speech signals efficiently. And these are usually called vocoders, and that is short for voice coder. They typically take speech, in the way I like to put it, rip apart the speech signal into the pitch part and the vocal tract part. They actually try to split that signal up into those two pieces. These vocoders are embedded in cell phones, and in particular they use very efficient ways at communicating what the vocal tract is, much more so than just sending the raw speech signal that you would normally do if you just had some regular old 6 or 7 kilohertz signal. Now it turns out vocoders have slipped into the music arena, and I'm sure if you've heard modern hip-hop, what they're doing is exactly what a vocoder does. They're ripping apart the signal into the vocal tract part and the pitch part. They're playing with the pitch signal a little bit, distorting it from being a pure set of pulses, and then putting it through a filter that looks like the vocal tract they measured, and it turns out the music sounds, at least to my ears, weird. But that's how vocoders work. And by the way, a few modern computer technology and signal processing systems are such that you can do this in real time. You can actually do this while the singer is singing. It's kind of interesting. But for our purposes, what they're doing and what's important is they're exploiting this special structure of speech. And you will learn that the more you know about signals, the more effectively and efficiently you can communicate those kind of signals.